Hello students. In this video I'm going to show you a nice, quick, easy way to compute the inverse of a 2 by 2 matrix. I'll show you the general formula and actually how you could derive it if you want to see the details of that. I'll do that rather quickly, and then I'll give you an example of how to go about computing the inverse of a 2 by 2 matrix. Alright, so here's our 2 by 2 matrix. And the first thing I'm going to do is, I want to compute A inverse. So I'm going to set up this augmented matrix where I have A, B, C, D. I could have put, A11, A12, A22, and A21, but I just find it easier to remember if I just put in the entries A, B, C, D for the 2 by 2 matrix. Anyhow, I go back to this augmented matrix and I have A, B, C, D on the left hand side, and I have 1, 0, 0, 1, the identity matrix on the right hand side. And then remember, we're going to try to convert this left hand side to the identity matrix, and by performing elementary row operations, and the resulting matrix on the right hand side will be the inverse of the matrix. And recall that the interpretation of that is that we're solving actually two systems of equation. One is where 1, 0 is the right hand side, and you solve that system of equations, you're going to come up with a column vector here, which will be your solution, so that when you multiply that column vector by this matrix, you'll get 1, 0. And then likewise, you're solving another system, you have 0, 1, so that when you get a resulting solution that is a column vector and you multiply that column vector by this matrix, you get the vector 0, 1. However, we just interpret that as we're going to find out the row operations needed to turn the left-hand side into the identity matrix, and then the resulting matrix, the result of performing those operations to the identity matrix will give us A inverse. Here we go. So I perform the following row operations, and I want to zero out the C, so I perform this operation. Then I want to zero out this B, working my way back up, so I perform this operation. But what I do here is I just find a common denominator, AD, so I multiply A times D divided by A, and then that's the common denominator is A, and then I just take the reciprocal here, because if I have B divided by this fraction, it's the same as B times the reciprocal of this fraction, so I get AB over AD minus BC, and then I multiply that by minus C times A, and I add that to this resulting matrix here, and then of course I get this result up here. Now I clean this up a little bit, so what I do is 1 could be written as AD minus BC over AD minus BC, but if I'm taking minus BC plus BC, I just get AD, so that's how you get this upper entry here. And then I just left this matrix here, this column entry alone. And now I have the result here on the left-hand side. So if I want to clear out this A, I multiply everything by 1 over A. And that will clear out the A's in the numerator and give us a D and a minus B in the numerator, all divided by AD minus BC. And then if I multiply this entry by its reciprocal, then the A's, of course, will cancel. Actually, I won't. Oh, yeah, that's right. If I multiply by the reciprocal, then the A's will cancel, and I'll get minus C over AD minus BC. And then if I multiply this by the reciprocal, I get A over AD minus BC. Okay, so you get this result for the inverse, A inverse. I encourage you to actually try to do, if you really want to see how this works, go through these calculations yourself. And you can use my result here to double check your work. All right, so the thing that you really want, though, is the formula, right? So this is the formula for A inverse, and notice that AD minus BC, which is the determinant of the matrix A, is common to all of these entries. So I'm going to factor that out. So to compute the inverse of a 2 by 2 matrix, you first compute the determinant, AD minus BC. Notice that if the determinant is not 0, then we expect the inverse to exist. If the determinant is 0, then the inverse does not exist. Okay, so first compute the inverse, and then you'll multiply the matrix by 1 over the inverse. And then what do you put in here? Well, let me just show you a mnemonic for, or tell you a mnemonic for remembering what these entries are. Notice that this diagonal AD here I'm just going to reverse those two for this diagonal. For the main diagonal, we're going to reverse the entries. For the other diagonal, because normally when we go in the left direction, we normally get a minus sign, and so you won't swap those entries. You'll leave them alone, so you'll leave B and C intact, but you'll hit them with a minus sign. All right? So that's the way I remember it. You might come up with your own mnemonic. So to compute the inverse, I swap the entries in this direction, the down to the right direction, and then the down to the left direction. I leave the entries in place. I just change the sign, because that's typically what we do in the down to left direction. We multiply by a minus sign. So let me just show you a quick example. So let's say you have this following matrix. You want to compute its inverse. So I'm going to compute the determinant, and it's of course going to be minus 2 times minus 7 minus 3 times 5, which gives us a minus 1. So I'll end up multiplying everything, 1 divided by minus 1, I'll end up multiplying everything by a minus 1. What do I do with these entries on the diagonal? I swap them. On this diagonal down to the right, I swap the minus 7 and the minus 2. And then the entries that go down to the left, I just change their sign. And so instead of having 3, 5, I get a minus 3, minus 5. And then I end up multiplying everything by a minus 1, so A inverse is equal to 7, 3, 5, 2. And then you can, in fact, check your answer, multiply A times A inverse, and you see that you do, in fact, get the identity matrix. 7 times minus 2 is 14, minus 14, plus 15 is 1. 3 times minus 2 plus 2 times minus 3, of course, will give you 0. Likewise, 7 times 5 minus 5 times 7 gives you 0. And 3 times 5 is 15, minus 2 times 7, which is 14. So 15 minus 14 gives you a 1. Similarly, if you were to take A inverse times A, you'd get the identity matrix. All right.